Today's lesson, we're going to talk about the properties of transformations. It's sort of like an introduction to transformations. The idea is that we're going to start off with a pre-image. This is our original figure. We're going to end up, through some sort of transformation, getting to an image. Generally speaking, if we talk about PQ, this segment, it will be transformed into P prime, Q prime. Some sort of movement will take place. We're going to move each of these points, P and Q, the exact same amount in the exact same direction. So there's kind of like almost like an arrow that goes between these 2 points from P to P prime. And if there was another point, like there was a W over here, we go to W prime. And they'd each move the same exact amount in the same direction. Okay? This is called an isometry. Another name for an isometry is basically a congruence transformation where it preserves the length and all of the angle measures. Specifically today, we're going to talk about using vectors to describe transformations, specifically translations. So a vector is something that has both direction and magnitude. Okay, so that's going to be the size. A lot of people will try to say, well, a vector looks a lot like a ray, and it does. When you look at it, if you look at this picture down below from F to G, that does look like a ray. The difference with a ray is that a ray is going to be, it has an initial point, and it goes in the direction in one direction forever. So it has basically just direction. A vector both has direction as well as magnitude, basically meaning that it's going to stop at some point. It has a terminal point. So again, as we look at this, there's the initial point, there's the terminal point, and the idea here is that we're going to write it as that. So wherever it starts, F, and it goes into the direction of G, and it ends at G. So we write this as FG, a little half arrow above it, and we pronounce it vector FG. Another thing to note is that we can talk about the horizontal component. That's basically how far right or left it goes. We'll mention this as a positive number if it's to the right, a negative number if it goes to the left. Vertical component is how far up or down it goes. It'll be a positive number if it goes up. It'll be a negative number if it goes down for the most part. And what we can do with those is in component form, we can talk about vector component form. It combines these horizontal and vertical components so we get something that looks like this. So we're going 5 to the right and up 3. It looks a lot like the point 5, 3, which means basically that from the origin we go over 5 and up 3. But instead of that, it's the idea that it's a vector. So it'll have these little angle arcs here, 5, 3, to kind of show that we're moving 5 to the right and up 3. If these were negative, that'd be 5 to the left and then 5 down if they were negative. There's kind of a neat picture here that was in your textbook where it talks about having the pre-image ABC, and then the vector that's going to talk about the translation is here is in purple, and basically each one of these is the exact same length, it's going in the exact same direction, and it will then produce the image A prime, B prime, C prime. Okay, let's talk about how we can apply some of this. It says use the translation, and here's a rule, translation rule for us. This basically means that to our x-coordinate, whatever we start with, we're going to subtract 5 to get our image. Whatever happens with our y pre-image, we will add 8 to it, and that'll be our image. So we'll say b prime. Here's 4, we'll subtract 5, that'll give us -1. Here's 2 plus 8, that'll give us 10. Similarly in D, we'll call this D prime. We're transforming into D prime. So -1 minus 5 would give us -6. 5 plus 8 would just give us 13. Number 3 is going to switch things up. Instead of saying image, what is the image of this? It says what's the pre-image. So that means we have to go backwards. So they give us F prime. It's our job to determine what F is. So F, instead of taking -3 minus 5, we're going backwards. So -3 plus 5 would give us 2. -4 minus 8 would give us -12. So we do the opposite operation up here in order to get from the image back to the pre-image. And notice I note that the pre-image is always just F, the capital letter, and the image is always the capital letter with a prime, pronounced F prime. In this case, we'll go backwards with H. H is 7, so we'll add 5 to that. That's going to give us 12. -5 minus 8 gives us -13. The image here, now we're going to go forward, so J prime So 0 minus 5 is negative 5. 2 plus 8 gives us 10. And why not, we'll just do the last one here. We're going to do the pre-image. So k, that's negative 4 plus 5 gives us 1. 6 minus 8 gives us negative 2. That's awesome. Okay, let's look over here. Write the rule for the translation. When you write translation rules, that's basically this underlined part up here. You always have to have an x comma y. There's always an arrow, which is pronounced maps onto. And there's usually an x plus something, comma y plus or minus something. I guess that should be it. That is either plus or minus something. And this is where you have to think about the ups and downs and lefts and rights. So let's do number 8 and 9. Number 8, we start off with x comma y maps onto. We're just going 3 units down. So that does not affect us horizontally, so we'll just leave that as x. But going down means we're just going to go y minus 3. Let's check out number 9. Number 9 says we'll start off with x comma y. That's going to map onto. It says 7 units to the left, so that's going to be x minus 7. And then 4 units down, that's going to be y minus 4. There it is. Those are our rules. And we could have done 7 and 10, and I just figured not to. Again, I don't really want to do number 11 either. It says triangle A prime, B prime, C prime is the image of triangle ABC. That makes sense after some sort of translation. First off, write a rule for the translation. So let's do that really quickly. Here's our rule. X comma y is going to map onto, let's see. So from A to A prime, what happens? It looks like we move this direction, and then we're going to move down. So let's look at our scale. Since our scale is 2, that means I'm going to go over 1, 3, 5, 7. So I'm going 7 to the left, so it's going to be minus 7. And then I go down 1 full block, which is also going to be 2. So I'll say y minus 2. So that's my rule. Next, and that should be the same rule if I go from B to B prime and C to C prime. It should be the exact same rule. Those are just the same movement should happen. It says then verify that the translation is an isometry. So the idea here, to prove that it's an isometry, what we need to do is we basically need to talk about why these two triangles are congruent. Since we have no angles we can work with, probably the easiest way to prove this is by the side congruence postulate. That's been a while. So what we'll do is we'll basically find the distance AB, and we'll just use the Pythagorean or the distance formula for that. So from A to B, let's see, we're going to go over 1, 2, 3, 4. We're going 4 in the horizontal direction, and we move down 2 this way, so let's do that. So that's 4 squared is 16 plus 4, so that would be the square root of 20, or that would be 2 square root of 5. That's awesome. Let's try A prime, B prime. We're going to verify that it's going to be the same. So we're going over 4. So that's going to be 4 squared. And then we're going down 2 again. You're noticing we have the exact same numbers when I'm doing this, so it should not take too much work. Square root of 20 equals 2 square root of 5. Okay? Because they're both the exact same length, that means side AB is going to be congruent to side A prime, B prime. I would continue this exact same process with BC and B prime, C prime, A prime, C prime, and AC. And what you do, it does check out. That's why it says say verify. You know ahead of time that it should work. You just need to actually show the work to make sure it works. Next thing, we're going to name the vectors and then write each component. We'll just name the vectors for each one of these. We start at M and we go in the direction of the arrow. So this is going to be MT. We draw a half arrow above it. In this case, we start at J and go in the direction of D. So this is vector JD. In this case, I start at R and I move down to S. So RS. Always the second thing, the thing that has the arrow like this. The thing that has the arrow is what's going to be second. So you always start where there is no arrow and go to wherever there is an arrow. And that's how you differentiate that. Let me just get those circles off of there. Next, when we're talking about the components form, so how do we get there? How far to the right do we go? Well, we're going to go over 4. So that's a positive 4. We go up 2. So that gives me a 2. Okay. For the second one, I am going to the right 5, and I'm going down 1. And for the third one, I'm not going to the right or the left, but I'm going down 4. So there's that. Okay, next. Triangle ABC has the vertices -2, 4. Well, there you can read them yourself. And it's translated to triangle A prime, B prime, C prime. Determine the translation using a vector in component form and determine the coordinates of the remaining vertices. Okay, so first off, we know that A is -2, 4. I got that from up in the picture here. And that's going to turn into somehow A prime, which is -5, 5. So vector component form, how do I get from -2 to -5? I have to subtract 3 from the x's. How do I get from 4 to 5? Well, I have to add 1 to my y's. So that's the vector component form to talk about how we're making this movement, how we're making this translation from this triangle, the original triangle, to the image, so from the pre-image to the image. Now I have to find the other points. So that's B prime and C prime. So let's do this, just the x coordinates first. It looks like I'm going to subtract 3 from the x coordinates. So 6 minus 3 is 3. For C, we have 3 minus 3, which is 0. Let's do the y's. The y's, we're going to add 1 to them. So that's 2 plus 1 is 3. And -2 plus 1 is -1. Kind of a sweet deal. Not too tough. Just remember that this represents your x movement. You're changing your x direction. This represents your change in your y direction. Okay, let's try some sort of story problem just to kind of make things a little bit different. It says a skier travels from point A to D, so they kind of go this way. And at points B and C, the skier changes direction as shown in the diagram. The distances in the diagram are in kilometers. Okay? So first off, it says write the component form of vector AB, BC, and vector CD. So let me just write this. Here's AB. How do I get from A to B? Well, to get from 0 to 2, I have to add 2. To get from 0 to 4, I have to add 4. That's pretty straightforward. For BC, let's see. To get from 2 to 7, I have to add 5. To get from 4 to 6, I have to add 2. Next, I have CD. What I'll do here is I'll just say to get from 7 to 10, I have to add 3. To get from 6 to 5, I actually have to subtract 1, so that's going to be a negative. Okay, what is the total distance the skier travels? That means I need to find the distances of each of these. Since this first coordinate basically talks about my distance in my x direction, when I set up a sort of a distance formula, I can basically use that. That's going to be 2 squared. Since the second component, the y's, are change in y, I can just say 4 squared. Again, that's going to give me the square root of 4 plus 16, so that's the square root of 20. Since I'm going to have to probably get these in decimal form, I'll leave it like that as opposed to simplifying. This will be the square root of 5 squared plus 2 squared, so that would give me the square root of, let's see, 25 plus 4, 29. And this distance would be the square root of, let's see, that would be 3 squared plus, and make sure that when you do this, you put it in parentheses, so you get a positive 1 back, so that's going to be 9 plus 1 equals the square root of 10. Okay, so I'm going to take these numbers, I'm going to add them in my calculator, just so I can get a nice number. You can't actually combine any of these. These do not combine at all, so you would get just exactly what it looks like, square root of 20 plus square root of 29 plus the square root of 10. And that's not really in a good form. It doesn't really give us any idea, but if I round to the nearest tenth, I would get 13.0 kilometers. So that's the total distance round to the nearest tenth of kilometers. So that's 23. 24 says, suppose the skier went straight from A to D. Okay, so they're going from here, like so. Well, probably a little bit straighter than that, but you get the idea. Write the component form of the vector that describes the path. So the idea here, this would be AD is what we call our vector. Okay, and the component form to get from 0 to 10 is just going to be 10. To get from 0 to 5 is just going to be 5. It won't always be that easy. And what is the distance? Well, distance equals the square root of 10 squared plus 5 squared. 10 squared is 100 plus 25, so that's 125. I could break that down into 5 square root of 5, or if I was to approximate that, that'd be about 11.2 kilometers. Okay, so that's kind of what we're looking at. A lot of this is we're talking about vectors. The vectors are going to describe our movement. Remember, with this idea, this is a skier. It's the same skier. It's the same skier whether they're at point A or B or C or D. It's just describing some sort of movement. Another interesting application of this might be video games. Whenever you see anything move across the screen or whatever, there's usually going to be some sort of, if you're a computer programmer, there's going to be something that looks similar to a vector in your programming when you're actually doing this. So another application of just any type of movement mathematically is talked about, usually using vector notation.